Hi, my name is Daniel Blackburn, and today we're going to talk about anaerobic digestion or anaerobic biodigestion or biodigesters, commonly called. Biodigesters or anaerobic digestion is a process of treating organic wastes, normally a slurry or a mixture of solid organic waste in water, and or any slurry that contains a high load of organic matter. Such as manures, for example, biosolids from wastewater, food waste can be prepared and used in these situations also, or other residues from industry or urban waste. In that process of anaerobic digestion, we find that we produce biogas and digestate. Digestate is the resulting stabilized organic matter from this process that can be used for agriculture. And the biogas can be an energy source. Therefore, anaerobic digestion is considered a sustainable energy management technology more than an organic waste treatment technology. But we are going to talk today about this technology in the framework of organic waste management. So we're going to be more concerned about the digestate in the processing of organic wastes rather than in the production of biogas. So this process occurs naturally. We find this process in many situations in nature. Anywhere you have anaerobic conditions or anoxic conditions, better said, and high organic matter concentrations. Think about mangroves, for example, which the saturation of the soil leads to anoxic conditions, or swamps, or any kind of sediments, lake sediments, marine sediments, like you see here in this photograph. You have frozen methane bubbles on this ice because of the methane that is being generated on the sediments of this fjord or this lake. So we not only in nature we find this, but every time we produce a high organic matter concentration material, like for example in animal slurry lagoons, we have that these lagoons are constantly producing methane and CO2. And the biodigester process is just a way of recovering that methane, and the process is already naturally happening on these systems. Another situation we can think about of a biodigester is the landfills. Landfills are just depositing and compacting organic matter from not only organic matter, but municipal waste. And together with the municipal waste, there is a high load of organic matter. And because of that anaerobic conditions, you will be producing also methane and CO2. It's like a huge batch biodigester. And then if you put the drains for the recovering that methane, you can have energy generation from the landfills also. And this is a sort of a type of anaerobic digestion. But it's not what you think of when you think about anaerobic digestion. What you think of about anaerobic digestion is working with slurries and mixture, liquidish, pasty mixtures of solids in water. So in that process, you're producing the biogas. The interesting part of biogas for energy recovery is methane. The methane concentration in that process is usually about 60%, but can vary between 40 up to 75%. Carbon dioxide can be something between 15 and 60%, and we have 1 to 5% moisture content. Nitrogen can be up to 5% and 2%, and hydrogen, there are traces of hydrogen. Hydrogen sulfide could be up to 2%, but usually less than that. And some oxygen and other trace gases like ammonia, for example, can be found in the biogas. But the most interesting part of this is the combustible gases, which the main one will be methane, but you can also have some hydrogen sulfide that are combustible on that mixture. Hydrogen sulfide is highly undesirable because of the bad smell that it gives off. So is biodigester, is anaerobic biodigestion what you need? So there's some situations where this is obvious that it's very useful to have anaerobic biodigestion. For example, when you have confined animal feeding operations. So confined animal feeding operations usually produce a lot of slurry materials from the species of these animals, and these slurry materials are often accumulated in lagoons, and this is the only if you only cover this lagoon and recover that methane, it's only a surplus and a diversification of the economic activity for your farm. So it's highly desirable that animal feeding operations that you use biodigestion systems, anaerobic biodigestion systems. And the type of systems depending on the volume of the slurry and if you have sediment content on that slurry. So you want to avoid on that system, the more you can, the presence of sand and rocks on that system. If you have any concentration of sand and rocks, you might want to include also a sedimentation step. So the type of slurry and the type of organic matter that we are interested in for anaerobic biodigestions are the ones with low carbon to nitrogen ratio. And if we have high carbon to nitrogen ratio, this will not generate a lot of gas in the system. The reason being is that anaerobic microbes, they are not very well adapted for degrading fiber. So lignin, mannan, xylan, these things are usually not degraded during the anaerobic digestion, and that is all recovered on the digestate afterwards. But all proteins, carbohydrates, and fats, which is highly important, the fats are highly desirable in these systems, are all being converted into methane. And the minerals, the plant nutrients will stay behind on the digestate in inorganic form also. So the digestate will be highly nutritious for plants, but will have a much lower organic load. And the type of organic matter that will remain on the digestate will be different from the organic matter from a compost because it will be more rich in lignin and fibrous materials. So if you have any operation that you have high organic matter with low carbon to nitrogen ratio, and you have odor problems, that is already a symptom that biodigesters could be great for you in that situation. One of the things that you need to consider is if you need the biogas or if you don't need the biogas, or if the biogas will be of use for you to diversify the economic activity. If you can generate electricity and feed that electricity to the grid and get money back for that, that is a huge business opportunity for any situation where you can produce biogas. So one of the advantages of doing with biogas is you can accumulate that biogas, and by accumulating that biogas, you can generate the energy in the peak times where the electricity is more expensive. Yeah? And therefore, that will be very interesting economically. And you can do it for when your farm or your household is off-grid, far from any situation where you can have electricity or gas supply. Then you can use this the waste from the household and the animals in this household or small farm to generate electricity and gas for that situation. If you're off the grid or plugging in the grid, it's highly expensive. Maybe the biogas is a solution for you in those situations. So countries like Brazil, in the northeast of Brazil, for example, and India, biogas is highly popular for households of small family or family agriculture, small farms in this situation, both for processing human waste and animal waste. One of the things you have to keep in mind in these situations is that there is a high level of complexity on the operations, and you need to keep in mind that you have to learn and manage that system closely all the time. So if you're not prepared to dedicate some close attention for managing this operation, this will likely not be successful. So you think about maintaining the tank, heating, mixing, pumping of the slurry, maintaining the gas tight systems for the biogas. And also when you need to make some reset and clean up of that system, that is important that is being done appropriately. For some industry like breweries will have also some opportunity of doing this. And for these breweries or any companies that are generating a high load, organic load slurry, what they have to keep in mind is are they prepared, or they're interested in diversifying and operating this high complex system, and are they interested also in managing the risks, because any big operation of biogas, you have some risks of explosion. This is a flammable gas, so you need to take care also and manage the risks of explosions. So one other thing that you have to consider is when you have biosafety concerns, pathogenic concerns on your organic matter, maybe the anaerobic biodigestion is not what you need, because it will not be like hot compost. The hot compost will self-sterilize in a sense that will remove pathogens by heating the material. But in the biodigestion, this will be more like a mesophilic operation. You can operate it at thermophilic stage, but you need a lot of energy input. So normally it's not done at the thermophilic range, only at the mesophilic range. So if you have biosafety concerns, that will be a problem for you. So for example, the management of human waste recycling, it's of high concern also, the type of digestate that you have afterwards, because you do not have the heating on this. All right, so let's talk about the biological process of anaerobic biodigestion. So the anaerobic process, it's divided in several phases. So the first phase is hydrolysis, where anaerobic microbes will go for the easy carbon source, carbohydrates, protein, sugars, and they will use that. It will produce CO2 and will also produce some products of degradation of those organic molecules. So this hydrolysis is just breakdown of bigger molecules and into smaller compounds, and the microbes are recovering energy in that process. The second process is acidogenesis. So these are fermentation microbes, lactic acid fermentation and acetic acid fermentation microbes. They are producing, acidifying the medium and using this organic matter as an acceptor of electrons also. But these microbes are acidifying the medium quite a lot. And the problem of acidifying the medium is the last phase of methanogenesis is highly sensitive for low pHs. So you need to operate this in a balanced way and to not overload the system with organic matter, because if you do so, you will acidify the system. The phase 3, there is a group of microbes, especially Clostridium and Morella microbes. They are considered microbes that have biochemistry called acetogenesis. Acetogenesis is a process where these microbes will use the CO2 and the hydrogen gas and will produce acetate in that process. Yeah? So the acetogenesis, these microbes will use the CO2 and hydrogen gas and produce acetate. Now, the last process is the methanogenesis, where the methanogens will use the acetate and other molecules in this system and will produce the methane. The methanogens, they are archaea. Yeah? Archaea is different from bacteria. All the other phases here are bacteria, but the last phase, the methanogenesis, which is of high interest for this process, because generate the main flammable gas in this biogas, the methane. This phase is performed by archaea. And archaea, they like neutral to alkaline conditions, so around 6 to 7 is optimum for them, but up to 8, between 6 and 8, they will tolerate. Around 7 to 8 is ideal for this archaea. So if you have batch systems, you must consider there is a microbial succession happening, and the type of gas that will be outcome in the system and different steps will be dependent also on those microbial successions. And if you do not take care of the correct equilibrium on continuous flow systems, the correct equilibrium between these different phases, it will mean that the process can fail because of the balance between different microbial communities. Or if not fail, be less efficient in a way because the correct microbial communities are present or not present. The feedstock that you can use on the systems, you can a whole range of feedstocks. The most obvious ones are animal manures and human manures and slurries from these manures. The amount of biogas that you expect from these manures is about from 50 cubic meters up to 200 cubic meters of methane per ton of fresh organic matter. And there is one thing that we must emphasize is fats are highly desirable in this. If you add fats to the system, oils and fats, these will produce much more methane. You will have something around from 800 to 1,200 cubic meters per ton of fats. So these are the types of feedstock that you can use in this operation. Some of the parameters that you have to think about when you're dealing with biodigesters is some things that you can regulate and tweak, and you must take them into account for the correct operation of these biodigesters. The first one is the organic load that you have. And you think about this organic load as volatile solids. What are volatile solids? Volatile solids are the fraction of the organic matter which can be converted into the methane. So usually it's around 90%. It will vary, but it's around 90% of the total solids. So you must consider the total solids on your mixture, but also the percentage of these total solids that can be transformed into methane. So if you have something with high carbon to nitrogen ratio, these volatile solids will be much lower. But with low carbon to nitrogen ratio, you could expect something around 90% of the total solids will be volatile solids. And the rate of feeding these biodigesters that you should think of, and this is important on the design of that system, is between 2 and 5 kilograms of volatile solids per cubic meter of the reactor per day. The other thing you must think about that is important on this management of this system is the hydraulic retention time. The hydraulic retention time is the number of days that this material must stay inside the reactor and before you can take off the effluent or the digestate at the end. The hydraulic retention time varies greatly between different systems. And if the most efficient systems will have like 2 to 4 days, but usually the retention time is between 20 and 40 days. So you imagine these systems are slow on decomposing this organic matter, much slower than aerobic processes. And you must consider the volume of these parameters between 20 to 40 days hydraulic retention time that will enter in the calculation of how big the volume of your biodigester should be to operate the full load that you have of organic matter on your system. Always remember that organic matter must be a low carbon to nitrogen ratio. Between 15 and 25 is ideal for biodigester. If the carbon to nitrogen ratio is higher than that, then you must think of other systems of recycling that organic waste. This system also, you should think about that if you have manures, or these usually contain already the methanogen community. But if you do not have manures or treated wastewater, you will need to inoculate the system. And a good way of inoculating the system is with the same digestate from an ongoing operation. So if you are starting a system and you believe that you do not have the appropriate microbial community on that system, then you should think about inoculating it with digestate from an ongoing operation. Other things that you should think that you can regulate on that system. One is the temperature. Yeah. So if your operation is in the tropical area or hot climate, you can get away without any heating on this system. So in Brazil, for example, in India, and even here in Oman, you can have this operation without any heating because the air temperature is already usually between 30 and 40, and the microbes will thrive really well within those mesophilic conditions. But in subtropical areas where you have cold winters, that will be very hard, and you must take care of having a heating on this system. If the temperature drops below 30 degrees, the operation will be, the amount of gas being produced will be much lower, and you must increase the hydraulic retention time in order to have this working in an appropriate way. You can also operate this system in the thermophilic range up to 60 degrees Celsius. The community will be slightly different, but you will be able also to remove pathogens. So the disadvantage of operating the system in a thermophilic range is because of the high energy input. So you want to operate the system at the mesophilic range because you don't want to spend a lot of energy. It will decrease the efficiency of the system if you operate this in thermophilic ranges. So the next thing you have to monitor, the next parameter that you need to monitor and care about in the system is the pH. Yeah? Something between 6 and 8 is acceptable, but optimum is always around 7. If you overfeed the system, you will have a problem of acidifying it. If your pH rises because of any other abundance of bases of nature of your organic residue, if the pH rises above 8, what will happen? You will have problems of ammonia toxicity to the microbes. So you need to monitor the pH and take care of the pH because actually you are growing these microbes. You need to provide the correct range of pH for them to have appropriate growth. So let's talk about the different systems that we have. The most simple one is a batch biodigester. You can have that like a barrel, like you see here in this photograph. And you can use those batch barrels where you load the system and leave the system operating closed up until it's completely, all the methane that can be generated is already generated. And you can have those batch systems in tandem, but normally this is not a good way of managing it. It's not the most appropriate way of managing it. The best way of managing the systems is continuous feeding and continuous flow of the system. In the continuous feeding of the system, the most simple way is covered anaerobic lagoon design. The covered anaerobic lagoon design, usually in animal farm operations, you already have the slurry lagoons. You just have to hire a company to cover that lagoon with a gas-tight system, normally with a flexible top, and that flexible cover will accumulate the biogas, and then you can use that biogas with a gas pump and connect that to generators and motors, or use that for heating if it's the case that you need. So this is a very simple system, the covered anaerobic lagoon, but it's easily said than done, because all this maintaining the system airtight is also hard, and it's better not to improvise. It's better to hire a company to do this in an appropriate way, in a very appropriate way. The other system that is very common, especially for small households or small farms, is the floating drum system, like the one you see here in the photograph. So this floating drum system is the only system that I personally have contact with. They are implemented widely in the northeast of Brazil by NGOs like Diaconia, for example. And these floating drum systems, they consist, and you have a mixing tank, and that mixing tank is where you have load that slurry into the reactor, and that reactor usually will contain like a barrier to avoid the slurry to go out immediately when in the outlet, and the outlet will take off the more processed material that goes over that barrier. In the top of this system, this is what it configures the system as a floating drum. In the top of the system, there is a reservoir, inverted reservoir, which will contain the gas. And this reservoir is free, is not fixed on the walls, and which means that the more gas is being produced, this reservoir will go up. And if you produce less gas, or if you use the gas, this reservoir will go down. So this floating drum works like a storage of the gas on this system. And every time you add more slurry, immediately some of the effluent will go out in the overflow tank. So there are many systems, many designs for this, but here are some photographs of some of these that are usually done, can be made with cement or concrete in the floor, or also can be made like with fiberglass in systems, and can be used for a mixture of in a substitution for a septic tank in a household, and also can include animal manures in this system for a higher generation of biogas. These type of systems are popular in countryside, where you have off-the-grid houses, where you have low access to gas and electricity. So this will be a way of these households, instead of using wood for cooking, they will use the biogas from the household for cooking. This is another type of system that can be used for households, which is called the bag digester. And the bag digester is just as the name suggests, it's just a big bag. And there is similar systems that are used in higher and bigger operations. It's called plug and flow, which is just like big bags or fixed bottoms with flexible top. And it's a slow process with low efficiency, high hydraulic retention time, but also can be useful. The flexible top, it's different from the floating drum because it's flexible. It's usually you will need to replace this within 5 years, but also has the advantage of having this flexible accumulation of the gas. The next system, which is a little bit larger scale, is the complete mix system. The complete mix, you use impellers to mix the system, and these impellers are always, you need to spend energy in mixing this. By doing that, what you find is you can process a lot more waste by reducing the hydraulic retention time. This is usually what it's done for industries and wastewater treatment systems. If you have a wastewater, a slurry, which is very fine and with lower organic waste, then you can use a system which is based on biofilm formation. So you can have a bead system, plastic bead system, or other types of beads where a biofilm of the anaerobic microbes is formed on the surface of these particles, and that can work as also an aerobic biodigester. These anaerobic microbes, they're very good in forming biofilms, and by forming these biofilms, there is a good distribution in space of those microbes and allows for operating with more liquidish type of slurry materials. These fixed film systems, or the name of them are fixed film systems. Yeah? They're not ideal when you have heterogeneous materials like slurry from animal waste, but for wastewater treatments they can be used. The other thing you have to take in mind, not thinking about how you cover the system anymore, if it's a flexible top or a floating drum, but how you mix that material. Yeah, so you had that impeller in the complete mixed systems, but you can think about other ways of doing this. And one of the ways of doing this is by pumping the biogas in the bottom of the reactor, and the other way of doing this is by pumping the inflow slurry on the bottom of the reaction in the reactor in a way that inflow will mix and remove that heterogeneity on that system. This mixing is highly important when you have heating. If you have heating on the reactor, that uneven distribution of the heat is undesirable for the operation of the system. So what you actually want is, you don't want to have some places that are too hot, in other places that are too cold, or you don't want that heavy sediment to form on the bottom and accumulate, because if you do that, if that heavy sediment accumulates on the bottom, you will need to dislodge this system more often. So pumping the gas on the bottom or pumping the influent in the bottom will allow for this mixing. And this system is called upward flow anaerobic sludge blanket, or UASB. Let's talk about maintenance. Yeah, the small systems need maintenance also, but the big systems you have to take care about several things. Yeah, some of the things that you have to take care of are sludge removal. Usually you need to dislodge the system every 2 years. The most efficient systems, they can last 10 years without dislodging, but between 1 and 2 years you will need to dislodge the system, and that dislodging can be costly also. You must include those costs in your plan, in your financial plan. The maintenance of the pump, the engines, and clearing of the pumps must be done between 3 to 6 months. And you need to do a replacement of iron packing because of the hydrogen sulfide corrosion of that system. There's a lot of hydrogen sulfide corrosion in these anaerobic digesters. Other things you must do often is valve leak checks, pipe leak checks, and the leak checks for the fittings also. As we mentioned before, the costs of the systems for very small systems between 1,000 and 5,000 for a small household, for a family, for a small farm. But if you have operations from hundreds of animals, you probably will spend something between $400,000 and $5 million per farm, and the average cost of a system for a farm is 1.2 million. So it's quite expensive. And if you consider that cost transferred for the biogas, what will happen is the cost of the biogas will be similar for the cost of a natural gas purchase. So it is not a huge benefit. It can be a benefit if you are off the grid, if you are far away and you do not have access to this. But in general, the cost of the biogas will be similar to the cost of the natural gas because of this high investment cost. The digestate. The digestate is usually applied for soils, agricultural soils, as a slurry. And there are different systems. You can use it with tractors, as you see here in these photographs, or you can use it also with irrigation systems that are prepared for pumping these slurries into the fields. Usually the farms that have animal operations already do this before implementing the biodigesters because they have their slurry lagoons. So this is not usually an extra cost or an extra benefit for that matter, because the nutrients that you will have from the slurry lagoon, you will have from your digestate all the same. But your digestate, don't count on your digestate as being able to sell it, because the appearance and how easy it is to work with is not the same as it is for compost. The compost is a darker, more fluffy material than the digestate. The digestate is more mineral and more fibrous material, and with a lot of inorganic nutrients in that system. But the digestate doesn't look as nice as a compost looks. So if you're using in your own farm, that is great material for using, but it's not something that you could count on as an income source. So I will link all the source of these materials on the bottom. And this is all I have to bring for you today. And I hope you enjoyed the lecture, and see you in the next one.